Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover accelerated encryption with wolfSSL and STM32 MPUs. Presented by wolfSSL embedded software engineer Andrew Hutchings and STMicroelectronics product marketing engineer Mena Roumbakis. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Andrew and Mena will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfSSL.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,500 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as WolfBoot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I'd like to turn it over to Andrew and Mena to discuss accelerated encryption with wolfSSL and STM32 MPUs.
Hello and welcome to this webinar on accelerated encryption with wolfSSL and STM32 MPUs. I'm Andrew Hutchings. I'm an embedded software engineer at wolfSSL, and I'm here with Mena Roumbakis from STMicro. So today we are going to be having quite a short agenda here. We're going to be introducing the STM32 MPU series of chips. They're a little bit different to the MCU series that you might be used to. I'm going to give a quick introduction to wolfSSL itself. I'm then going to talk about the work we've done with wolfSSL on the STM32 MP135F chip and the STM32 chip. And we'll have a Q&A session at the end of this webinar. So to start off, I'll hand over to Mena, who's going to give you an introduction into the STM32 MPU series.
Thanks, Andrew. I'm excited to join you today to talk about our MPU portfolio and the additional security that wolfSSL can bring to our ecosystem. As Andrew mentioned, my name is Mena Roumbakis, and I'm an STM32 product marketing engineer focusing on our security and MPU offering in the STM32 ecosystem. Here we can see the full STM32 portfolio, including some of the expanded or new series in the STM32 family highlighted in green. That includes the near threshold ultra low power STM32U3 and the STM32N6, which is our first microcontroller with a dedicated AI accelerator. Today we're going to focus on the MPU offering, which includes the STM32MP1 and MP2 devices that are in the top row. And here we can see a more detailed view of the STM32 MPU portfolio. The STM32MP1 was released in 2019, followed up with the low-cost STM32MP1 Both of these devices are based on Cortex A7 cores, and the MP1 has a Cortex M4 processor as well. In the second half of last year, we released the STM32MP2, and just recently we announced at Embedded World in 2025 the release of the STM32MP2. In the second half of this year, we have a lower cost STM32MP2 coming as well. These newer devices are based on Cortex A35 cores that run up to 1.5 GHz and have Cortex M33 processors as well. Andrew today is going to talk to you about the STM32MP1 and the STM32MP2. And finally, we can see here some of the individual products across our MPU portfolio. The devices cover a wide range of cost, power consumption, performance, and applications. Andrew will talk more on the very cost-effective MP1 devices shown in the bottom left that are based on a single Cortex A7 core and can operate up to 1 GHz. In addition to the MP13, you can see the single and dual core variants of the STM32 MP15 devices, which are also based on the Cortex A7. The MP25 devices that Andrew will also discuss were released in the second half of last year and are shown on the top and are based on single or dual Cortex A35 with an additional M33 core. And as I mentioned on the last slide, we now have the STM32 MP23 devices available, which are similar to the MP25 with some performance trade-offs at a lower cost. And then in light blue, we can see the upcoming STM32 MP21 devices that will be available in the second half of this year and will offer our most competitive price point in the MP2 family. Our STM32 MPU processors are designed to be general-purpose MPUs with a focus on complex and industrial applications. It does include rich interfaces for growth and connected applications, a very efficient MPU with advanced compute capabilities, and strong security from the ground up. I will discuss some of these security features in the upcoming slides, and Andrew will showcase some of the wolfSSL security stacks running on these processors as well. As I said earlier, the STM32 MPU devices are geared towards rugged and industrial applications. Included in that is the 10-year longevity commitment from our STM32 portfolio. So every device is committed to be manufactured for 10 years, and that is on a rolling commitment that is renewed every year. In addition to that, we have extended operating conditions as well. We can operate at 100% on time for 10 years at junction temperatures of -40 C to 125 C. This allows us to operate in very harsh conditions. Our latest STM32 MP2 series includes advanced edge AI capabilities. Take advantage of our dedicated hardware AI accelerator that can operate at up to 1.35 TOPS. Our ecosystem is flexible so that AI can run on the CPU, GPU, or the NPU or AI accelerator. To take advantage of the AI accelerator, we also have advanced multimedia capabilities. This includes a 3D GPU that supports up to 1080p resolution with a full HD video pipe outputting to RGB, LVDS, and DSI outputs, and a MIPI CSI2 camera interface with image processing pipeline. Some additional features of the MP2 family include a 3-port gigabit Ethernet switch on the fully featured MP257 device, and the 3D GPU I mentioned can operate up to 900 MHz and supports OpenGL, Vulkan, OpenCL, OpenVG, and OpenVX with up to 138 million triangles per second. We also have a video encoder/decoder that can handle H.264 video at a full HD at 60 frames per second with dedicated video RAM. The display controllers I mentioned can support up to QXGA resolution displays at 60 frames per second. And the image signal processor can operate up to 5 megapixels at 30 frames per second. It provides black level calibration, contrast enhancement, exposure control, along with color and format conversion and statistical extraction. As I mentioned, the STM32 MPU processors are designed to be general-purpose processors with a wide array of applications, and here we can see just some of those potential use cases. This slide shows 3 potential target markets for the MP2 family: industrial, smart home, and smart city. That could include gateways, PLCs, and barcode readers in the industrial space, white goods, HMI applications and doorbells in smart homes, and power grid and EV charging and metering in smart cities and infrastructure applications. In addition to the target markets, we also want to showcase some of the potential use cases for AI in these applications, such as anomaly detection, facial recognition, people and object detection, along with traffic and energy management. There are many potential use cases for AI across multiple segments, and we strive to give you a strong solution with the AI accelerators and a robust ecosystem to bring those designs to completion. To ensure the safety and integrity of both your product and the IP or intellectual property, we've built our MPU portfolio on top of a very strong, secure ecosystem. And now I'd like to dive into some of the security features of the STM32 MP2 devices. First, I would like to mention that the devices are CSIP Level 3 and PSA Level 1 certified. We can achieve these certifications thanks to the hardware features, which include memory and peripheral protection against illegal access control, which is part of our RIF, or Resource Isolation Framework. There's a secure hardware crypto accelerator, which has additional hardware features to prevent physical attacks, and we can provide device authentication and attestation during the full product life cycle and have code isolation for runtime protections. Now on the right, you can see additional capabilities of our STM32 security ecosystem. We have Opti, which I describe as a microkernel that provides security services during runtime. We also provide a secure secret provisioning process, or SSP, which allows you to securely provision your device during manufacturing. And to help facilitate that, we have our STM32 Cube framework for MPUs, which helps with key signing and key generation. And here we have some additional hardware security features of the STM32 MP2 devices. On the left, we can see some of the hardware protection. We have 16 tamper pins that can be paired up to do 8 active tamper. We do temperature, frequency, and voltage monitoring that can be maintained over VBAT power. We also offer secure key storage with rooted trust stored in OTP memory. We have backup registers and secure backup RAM that's also available in the VBAT power mode, and a secure encrypted storage with our HUC, or hardware unique key. There's also on-the-fly encryption decryption on the DDR engine. In addition, we also have an OctoSpy port that can support on-the-fly encryption. This is all done in a secure BGA package so that the more secure pins are located on the inner ball out of the package. On the software side, we have the trusted execution. We provide trust on both the Cortex A35 and Cortex M33 cores. We have secure boot with trusted firmware for applications and trusted firmware for microcontrollers available, and Opti, which again is our microkernel providing secure services during runtime. All of this is secured with our resource isolation framework, which the analogy I like to use is access control lists in Linux. What that does for files, we do in hardware on silicon on the device with the RIF. We provide all these services during the full device lifecycle device, and we also have secure JTAG that requires authentication if enabled. And then again, as part of our ecosystem, we have the secure provisioning during the manufacturing process. The dedicated hardware crypto engine has 2 AES engines, DES and triple DES engine, SHA-256, SHA-3, and HMAC accelerators. And we also have AES, RSA, and ECC engines with side channel attack resistance. This prevents physical access attacks from working, such as differential power monitoring. We also have a true random number generator and a unique ID on every device. And with those final security details, I would like to pass it back to Andrew to cover some of the wolfSSL features running on both the STM32 MP135 and STM32 MP257 processors. Thanks for your time, and I hope you found this overview of the STM32 MPU portfolio helpful. Back to you, Andrew.
Thank you very much. So, an introduction to wolfSSL. It was originally part of MySQL. MySQL needed its own SSL solution due to licensing issues and a few other things. And what was born out of that was YASL, yet another SSL. And this was a C++ library that was built into MySQL and forked out into its own company called YASL. Later on, it was rewritten into C and called CYASL. And then in 2014, the name of the company and the product got changed to wolfSSL. I myself have actually come from a MySQL background, so I've been part of this whole journey the whole time. wolfSSL as a company has a whole suite of products revolving around the wolfcrypt engine. We have wolfSSL, the namesake, which is the TLS library, the MQTT library, wolfMQTT, an SSH library, a TPM library, a secure bootloader, a embedded IDPS, PKCS11 provider, and a software interface for HSMs. We have Wolf Engine if you have an old version of OpenSSL and want wolfcrypt to be the back end of that. We have Wolf Provider if you have a newer version of OpenSSL and want wolfcrypt to be the crypto backend for that. And then we have a whole bunch of wrappers, such as the Java wrapper, JNI, the C# wrapper, Python wrapper, JavaScript, and as well, Daniel Stenberg, who is the lead developer of curl, is employed by wolfSSL to develop curl and tinycurl and provide support around that. STMicro is, of course, an important wolfSSL partner. We are always adding support for the new hardware pretty much as soon as we receive it to the various wolfSSL libraries. And in fact, we have a goal for Wolf Boot in particular to have 100% support for all ST parts that are capable of running it by the end of the year. So wolfSSL on the STM32 MP135F chip. The 135F is a 1 GHz ARM Cortex A7 chip. It's got 128K of SRAM. There's no kind of flash built into the chip for general executables, but it does support up to 1 GB of DDR RAM. It's extremely feature-rich and versatile chip. I could really imagine this being used in kind of car and entertainment systems, that kind of thing. So we have added bare metal support for this, so with no OS whatsoever in wolfSSL 5.7.6. There's hardware HAL acceleration for random number generation, AES, and the various algorithms around AES, SHA-2, SHA-3, and ECC. It's available as a cube pack in STM32 CubeMX and STM32 Cube IDE. But as well as adding bare metal support, you can also run it in OpenSTLinux. It kind of just works. We really didn't have to do any changes to make it work with OpenSTLinux. There's 32 ARM and Neon assembly optimizations available, and we can do hardware acceleration for the board or the chip using CryptoDev built into Linux. STM32 CubeMX can only configure clocks up to 650 MHz inside the IOC editor. So if you want to go higher than that, the chip can go up to a gigahertz. Some manual PLL tweaking is needed. There are examples of how to do this in ST's example pack. There's definitely it is a 900 MHz example, which is very good. Cross-compiling using Linux for the MP1 series is relatively simple. You have to do it in Linux because the SDK is designed for Linux. But if you download the SDK, you CD into wolfSSL, you run the source command you can see on line 2 here to set up the environment. This sets up the compiler and the C flags and things like that. And you just run /configure with a host ARM v7 Linux GNU EABI, and you can enable the static if you want, and just run make, and you'll end up with a library ready to use, as well as examples compiled for the board. So it's live demo time. I'm going to be running through 3 demos on this board. The first is booting into the engineering bare metal mode and running a basic wolfCrypt benchmark. The second is going to be running a full RTOS, LWIP, TCP/IP, wolfSSL kind of setup. And then we're going to be running the wolfCrypt benchmark in OpenSTLinux. So for this demo, I'm going to be showing how to run the basic wolfCrypt benchmark on the STM32 MP135 FDK. Now, due to the limited amount of SRAM on the board, the first step is going to be initializing the DDR RAM on the board and then running the application. And the application is quite simple. We're essentially running the benchmark test function, as you can see here. And that's pretty much it. It's part of the code base inside wolfSSL, so it should be quite simple. Now, to initialize the DDR, there's an example application called DDR init. So we just click on this and click on run, and you should see the LED on the board flash blue, which means the DDR init was initialized successfully. And then we go to the application and we'll hit play on this, and that sends it over to the board as well. And then we go to running now. You can see the clock on this is running at 650 megahertz. That's the default for the DDR init setup. The board is capable of running at 1 gigahertz. And all of the benchmarks you can see here are using the hardware acceleration for those specific functions, if it can be used. That is the benchmark complete, and added a little red LED flashing at the end just to make sure that the board was still running at the benchmark completion. We can see it actually, a lot of these results are very, very fast, as to be expected when using the hardware acceleration on this board. This next demo is a little bit more involved. So what it essentially is using FreeRTOS combined with LWIP and wolfSSL to make an example client. Now what this is going to do is connect to an example server on my laptop. You can see the IP address listed here for my laptop, 192.168.7.243. The destination port is 11111, which is the example port used for wolfSSL's example applications. Now, the client on this STM32 board is going to send this test message here, TLS test 1 with stars. It's going to send it to the Echo server. The Echo server is going to bounce it back again, and then that's going to echo onto the terminal that we have open for the board. So as before, we need to initialize the DDR. So we hit the play button on that. And we get the blue blinking LED. Now we need to run the Echo server. That shouldn't show anything more than just that. And now we hit play on the example code. I'm just going to search for my DHCP server on my network, grab an IP address in a few seconds. There we go, and immediately connected. Did the TLS handshake and got the response back. Simple as that. Now for my last demo with this board, I'm going to be using the OpenSTLinux built into the SD card that comes with the development kit. You can see I've now booted into it. I've had to change the boot switches here to make that possible, but the SD card was already pre-prepared. I've compiled a version of wolfSSL with ARM assembly optimizations, so I can run the benchmark from here. I'm SSH'd into it from this laptop, and here we go. You can see the results are pretty good. They're not, apart from the RNG, which is using the kernel RNG for optimizations. In general, the performance won't be as good as what we were getting on the hardware accelerated bare metal if we were doing a clock for clock comparison. But we can do things like crypto dev, accelerations and things like that. We'd have to reduce the block size to do this. We're using a 1 megabyte block size for this, which on this chip with the Linux Dev Crypto accelerations is a little bit slow. But even with the ARM assembly optimizations, we are getting really, really good performance out of this chip in a Linux context. Okay, so the STM32 MP257F. This is a bit more of a beast compared to the MP1 series. You've got a dual 1.5 GHz 64-bit ARM Cortex A53 and a 400 MHz Cortex M33 on the chip. You've got support for up to 4 gigabytes of DDR4 RAM, and it's really an embedded multimedia powerhouse. This thing is pretty powerful. For Linux support, again, it just works for us. We've got 64-bit ARM and Neon assembly-based optimizations already baked into wolfSSL. And again, you can do hardware acceleration via the Linux CryptoDev device. Cross-compiling for the STM32 MP2 is very similar to what we were doing for the MP1. You still need a Linux desktop or laptop to do this, but you just download the OpenSTLinux SDK, CD into it, run this source command here to actually set up the environment again. The configure command is very similar, but it's arch64 Linux GNU EABI. And I've also enabled extra assembly optimizations here compared to last time. And just run make. And now it's time for another live demo. This time the STM32MP257F is going to be doing a Linux demo. We don't have a bare metal demo for this. At the moment it's a little difficult to set up this board for bare metal, so we're just doing a Linux demo. Now with the STM32MP257F DEK, you can see my model of it here. I've actually custom 3D printed a case for it because it was recently used in a demo at Embedded World. I didn't want people messing with the buttons and switches, but you still get to see all the blinky lights through the casing here. Anyway, I've SSH'd into it. I've compiled a version of wolfSSL with our ARM64 assembly instructions for this board. And as before, if we do run bench, we'll start to get to see results pretty quickly. And this being an ARM64 and it's a little bit faster in general than the MP1 chip, we're getting already much faster results than can be seen before. And I've added a few extra algorithms to this, which we'll see shortly. Now here's the start of the key algorithms we want to talk about. MLChem, and in a few seconds it'll also do MLDSA. These are post-quantum crypto algorithms that are part of wolfSSL. They are also ARM assembly optimized, so they run really, really fast. So if you're interested in post-quantum crypto acceleration, wolfSSL is the place to go for this. And thank you very much. That is everything we have today. It's time for a question and answer session. Please feel free to give us any questions you have.
Wonderful. Thank you so much, Andrew and Mena. To kick off the questions, if the CPUs have crypto algorithms in the hardware, why would I need wolfcrypt? My understanding is that wolfcrypt is a software library with crypto algos.
That is correct. But with wolfcrypt there, it's a standard API. So if you needed to switch to another chip at a later date, you wouldn't really have to change anything. And it's makes it easier to access these APIs as well. wolfcrypt API is relatively simple.
Wonderful.
There's one more thing too. This is David. Sorry. When you think about TLS protocols and what's being used underneath, not all of the algorithms can be offloaded to hardware. So wolfcrypt's able to fill in those gaps. And if you're using any algorithms that are not in hardware, of course. Sometimes we also find that our software implementation, our ARM assembly optimized versions are faster than what can be done in hardware. Sometimes, but not always.
Thank you, David. Is there any intent to certify the STM chips themselves for FIPS 140-3, i.e. the hardware crypto engines?
No, not the chips themselves. They won't go through the FIPS 140-3 certification process. It depends on the specifics, but that's not to say that a device couldn't be taken through a certification process, but ST does not do that for the hardware.
Amazing, thank you. You mentioned post-quantum encryption. Can you tell us a little bit more about that, Andrew?
Yeah, absolutely. So as we are reaching an era where post-quantum computers could be here in some say 5 years, 10 years, whatever, there are people scraping data right now that could be run through quantum computers and decrypted. So NIST have come up with a couple of standards, MLChem and MLDSA in particular. wolfCrypt already supports these algorithms, and we are very fast on acceleration of those. And in fact, we are giving a webinar with ST about this on April 23rd called Post-Quantum TLS 1.3 over UART. So if you're interested in post-quantum encryption, I highly recommend viewing that.
Great. Will there be production qualified software for HSM memory drivers?
Sorry, is that one again?
Will there be production qualified software for HSM memory drivers?
David?
I'm not sure what Mena, do you have any idea what he's talking about?
HSM might be the hardware secure module, but no, not. I don't think I could answer that now. We can follow up on that question.
Wonderful. Is there a handy reference for STMicro versus wolfSSL solution slash feature mapping on cybersecurity capabilities to help the design engineers?
So on the ST side, we do have some. If you go to our STM32 trust page, we do have some mapping of the security features you're looking to implement and what ST can offer. And I don't know that we don't have a combined one with wolfSSL, I don't believe, though, right, David?
Yeah, I don't think we have a single place that maps all of those features. There's different aspects to it. There's secure boot and then all the way into the application, the protocols. We try to make it real easy at wolfSSL by handling all of that under the hood, right? So if you're using our libraries, with the build options turned on, that it's transparent and used when it can be. But there's so many aspects to that, so it's a complicated question. Yeah.
Wonderful. Kind of going back to the post-quantum, does ST have a hardware accelerated post-quantum crypto?
Yeah, that's it's a good question. One I've gotten in the past, and to kind of expand on what Andrew said a little earlier, PQC is we're still relatively new. The NIST has made some progress in certifying algorithms. It's still a very fluid thing that they just recently approved yet another algorithm as well. Today we do not have hardware acceleration for PQC algorithms, but that's not to say that won't change in the future. It does take time for us to implement these features in silicon. We definitely don't want to introduce any potential vulnerabilities in hardware as well. And some of these algorithms are still working through some of the vetting processes as well. So this will change as we move into future silicon, but today we do not have hardware to accelerate PQC algorithms.
Wonderful. Andrew, I believe this one's directed for you. Is there support for the ST MPUs with Wolf boot?
So there isn't yet, but we do, as I mentioned actually earlier on, we do have a goal of covering 100% of the ST chips that will support Wolf boot by the end of the year. We relatively recently got the MP series boards, so we haven't had a chance to actually implement those yet, but it is high on our agenda.
Wonderful. Are all of the STM32 MPUs available now?
Yeah, so the MP1 5 DK board that Andrew used for the one demonstration, that's been available now for a couple of years. I believe it was released in 2022. And then just this end of second half of last year, and then just recently at Embedded World, we announced the MP2.5 last year and the MP2.3 very recently, and samples and boards are available for both of those. And as Andrew just mentioned, he just got some of the MP2 boards himself. So all those should be available through our channel partners.
Wonderful. Well, that wraps up the questions. Thank you, Andrew and Mena, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have questions, please reach out to us at facts@wolfSSL.com. Thank you again, and we look forward to seeing you on April 2nd for developing building secure embedded applications using wolfSSL and the MQX RTOS platform. Thank you all.